So over here, let's just start by looking at the derivative rules we have here. So if we have f of x to be equals to k, where k is a constant, so we're starting with a constant function first. Now, we know that constant functions, in fact, have a horizontal line as a representative curve. And you know that a horizontal line has a slope of 0 at all points of the line. So a horizontal line having a slope equals to 0, it means that the derivative of this function at any point is in fact equals to 0, because the tangent to a line is the line itself. So the tangent to this horizontal line at any point is that horizontal line itself, which has a slope of 0. So this is why whenever we are finding the derivative of a constant, the constant always has 0 as a derivative. However, similarly regarding a linear function, so if I have any line of equation y equals to ax plus b, as I've just mentioned, the derivative or in fact the tangent to a straight line is the straight line itself at any given point. So the slope of the tangent at any given point on this line would in fact be the slope of the line itself, which is a. So this is why whenever you're finding the derivative of a constant, that would be the slope of that linear, the derivative of a linear expression, that would be the slope of that linear expression. So if f of x is in the form ax plus b, f prime of x would actually be a. Now, this next one, I do have it in a box because it is like the most important rule. Now, as you will see that all the other rules would in fact come out of this one. They're particular cases of this one. So this is the power rule of derivatives. So in the power rule, whenever you have a term in the form x to the n, the derivative of a term in the form x to the n would actually consist of dropping the exponent and then subtracting 1 from the exponent. So the derivative of x to the n is x to the n minus 1. Now, going back to this example we had where we had f of x equals to x squared. Now, over here, this is in the form x to the n. So according to the rule that we've just seen, f prime of x would in fact consist of dropping the exponent and then subtracting 1 from the exponent. 2 minus 1 is 1. So f prime of x would actually be 2x. Now, going back to check the derivatives we have found graphically using the tangents. So f prime of 1, replacing x by 1 here would give you 2 times 1, which is a 2. And then f prime of 2 would be 2 times 2, which is a 4, which are the derivatives we actually found graphically. These are the values we have found graphically. So whenever you have a function in the form x to the n, to find the derivative, you'd actually drop the exponent and subtract 1 from the exponent. However, if I would move to the term in the form f of x equals to 1 over x. Now, in order to justify this derivative, over here, all you have to do is just use the power rule. 1 over x can be written as x to the negative 1. So f prime of x, using the power rule for n equals to negative 1, drop the exponent, then subtract 1 from the exponent. Negative 1 minus 1 is a negative 2, which is equivalent to negative 1 over x squared. So in fact, even if you have not memorized that the derivative of 1 over x is negative 1 over x squared, all I have to do is just know the power rule and then apply the power rule for n equals to a negative 1. Similarly here, for fx equal to square root of x, you'd notice the derivative is 1 over 2 square root of x. Now, why is it so? Because if f of x is square root of x, then f of x can be written as x to the half. So I could still apply the power rule for n equals to half. So the derivative here is, I drop the exponent, which is a half, then subtract 1 from the exponent. Half minus 1 is a negative half. So the negative exponent drops down to the denominator to become positive, and x to the half would actually be square root of x. So this is why the derivative of square root of x is 1 over 2 square root of x. Now, similarly here, if I had f of x equals to 1 over x to the n, now you'd notice that over here, f of x equals to 1 over x has this form for n equals to 1, or in the form x to the n for n equals to a negative 1. So this is in fact a rule to generalize finding the derivative of functions in the form 1 over x to the n. So over here, this could actually be justified using the power rule as well. So over here, you'd notice that 1 over x to the n can be written as x to the negative n. So finding the derivative here, drop the exponent according to the power rule, so negative n, subtract 1 from the exponent. So over here, negative n minus 1 can be seen as x to the negative into n plus 1. So the negative exponent, drop it down to the denominator, it becomes positive, and it would leave me with negative n over x to the n plus 1. Which you'd notice if you apply this rule for n equals to 1, if you apply this rule for n equals to 1 to determine the derivative of 1 over x, you notice that for n equals to 1, it's negative 1 over x to the 1 plus 1, so it's negative 1 over x squared, which is the same derivative we got here. So functions in the form 1 over x to the n, you could use the power rule to determine their derivatives by just considering the negative exponent at the numerator, or you could just apply this rule immediately. Now, some properties before we move to the examples. Now, over here, if you have a sum of two functions, the derivative of the sum is the sum of the derivatives, which means that the derivative of u plus v is u prime plus v prime. You find the derivative of u plus the derivative of v. And similarly, if this was to be a difference, so the derivative of a difference is also the difference of the derivatives. However, now let's just do the third property before 2 and 4. Now over here, if you have a function that is being multiplied by a constant, now the constant is not affected by the derivative, so it's just that constant multiplying the derivative of u. However, if we move to the derivative of a product and the derivative of a quotient, now for the derivative of a product, u times v is not u prime times v prime. U times v, the derivative of u times v or of a product is u prime v plus v prime u, which means it's the derivative of the first times the second plus the derivative of the second times the first. And similarly for the quotient, u over v, the derivative of u over v is not u prime over v prime. It's u prime v minus v prime u over v squared. So it's the derivative of the first times the second minus the derivative of the second times the first divided by the square of the denominator. Okay, so these are the product rule and the quotient rule of the derivatives. However, these properties that you see here are what we refer to as the chain rule of the derivatives. It's when you actually have to do two successive derivatives for the same function. For example, if you notice here, this looks very similar to the power rule. So over here, we have the function in the form u to the n. So the derivative is, we drop the exponent, subtract 1 from the exponent, but then multiply by u prime. Now, what does that really mean? So we've just seen that if you have x squared, to find its derivative, I drop the exponent and subtract 1 from the exponent, which is x to the 1. So the derivative of x squared is 2x. However, what if instead of x, you have a function of x? Suppose you have 2x plus 3 all squared. Now, this is in the form of a power, but at the base of the power, I do not have an x. I have a function of x. So this is what is referred to here as u. So what we're referring here as u in the properties of the chain rule is the actual base of the power that is different than x, which is a function of x. So over here, by considering u to be 2x plus 3, then u prime would be equals to 2. So if I were to go back to finding the derivative of this according to the chain rule, so it's in the form 2 times u, so I drop the exponent, subtract 1 from the exponent, but I should not forget to multiply by the derivative of the function of x I considered here as the base. So having set u to be 2x plus 3, then u prime would actually be equals to 2. So replacing u and u prime is 2 times 2 again, that's a 4, and u, which is 2x plus 3. And similarly, all the derivative rules that you have here, instead of x, if you have a function of x, which we usually call a u by substitution, so you would find the derivative exactly the same way, but then you do not forget to multiply by u prime. For example, square root of u would have a derivative of 1 over 2 square root of u, but times u prime, which is the derivative of the radicand of the square root. So, which you can see here. So over here, let's just move to solving some examples here. Okay, so if we look at the first one is simple. It's just a polynomial which consists of constants and powers of x. So to find the derivative here, all I have to do is just find the derivative of each term, because we've just seen here in the first property that the derivative of a sum or a difference is the sum or difference of the derivatives. And over here, this being a constant multiplying x cubed, so we just keep it aside. So it's negative 2 into the derivative of x cubed. Now, this is a power of x, so we drop exponent, subtract 1 from the exponent, and then that is a linear expression, 2 times x. Now that is linear, and we've seen that when it's linear, the derivative would just be equals to the slope or the coefficient of x, and negative 1 being constant, the derivative of a constant is 0. So f prime of x would actually be negative 6x squared plus 2. Okay, so moving on to the next one, f prime of x would be derivative of 2x. Now we've already found this derivative a couple of times earlier. So drop exponent, subtract 1 from the exponent, that would be a 2x. Now the derivative of 1 over x, you can just keep in mind that it's negative 1 over x squared. However, if you fail to remember that, you could apply the power rule and write it as x to the negative 1 and apply the power rule for n equals to negative 1, or keep it in the form 1 over x to the n and apply this rule for n equals to 1. They would both give you exactly the same answer. So it's negative 1 over x squared, and negative x being linear, the derivative would be the slope of that linear expression or the coefficient of x. So on f prime of x, you can just leave it as is or reduce to the same denominator and simplify. Now moving to the third one, you'd look at the third one. The third one is in fact a product of two linear expressions. And we've just seen that the derivative of a product is not u prime over v times v prime. U times v is u prime v plus v prime u. However, sometimes we have the chance to escape the product rule. For example, if we look at this, this is a product of just two linear expressions. We could just easily expand. And if we expand, we end up with a quadratic equation. So expanding here is practical, it's okay. So when you expand and write it as in its expanded form as a quadratic polynomial, all you have to do is just find the derivative term by term the same way you did here. Or you could just keep it in the form u times v and then apply the product rule. We're going to do it using both methods. So over here, I'm going to start with method 1, which is by expanding f of x. So f prime of x would, sorry, this is not f prime yet. I'm still working with f of x. Just keep in mind that you should not set a derivative equal to the function. Okay, so if you're still working on simplifying f of x, that's f of x, then when you need to find the derivative, you just start a new line and f prime of x equals. So over here, it's negative 2x squared by expanding, then 2x plus 3x, that's plus 5x minus 3. So this is f of x expanded and simplified. So f prime of x is, now this is the negative 2. I'm sorry, here it is. So negative 2 here is a constant multiplying x squared. So we just leave it aside for the second and we just differentiate x squared. Differentiate means find the derivative too. So the derivative of x squared is 2x. So drop exponent, subtract 1 from the exponent. Then 5x is linear, x is to the power of 1, so the derivative is just the coefficient there, and minus 3 is a constant, so its derivative is 0. So over here, simplifying this would give me f prime of x equals to negative 4x plus 5. Now that is the first method. Now the first method, which is done by expanding f of x, simplifying that polynomial, and then finding the derivative term by term. Then if I were to use the product rule as a second method, so over here, product rule. So I look at f of x as being the product of u and v. So over here, if this is 2x minus 3 into a negative x plus 1, so over here I have u to be 2x minus 3 and v is negative x plus 1. So u is 2x minus 3, then what is u prime? Now that is a linear expression, so the derivative is just the slope of that linear expression, and v is negative x plus 1, so v prime is negative 1. Now going back to the product rule, so f prime of x, now the derivative of u times v is u prime v plus v prime u. So replacing u, v, and u prime and v prime by their expressions, that would give me u prime, which is 2 into negative x plus 1, and v prime, which is negative 1 into 2x minus 3. So over here, expanding and simplifying, now negative 2x and negative 2x would give me a negative 4x, and 2 plus 3 would in fact give me a 5. So you'd notice we ended up with exactly the same derivative. However, since over here this is just consisting of a product of two linear expressions, then maybe expanding would be the easier way to find the derivative. So sometimes we could escape the product rule or the chain rule, but sometimes we can't. So we're going to see in the next exercise that sometimes we cannot escape the product rule. So over here, if we look at this example here, we have f of x equals to 2x plus 3 all squared. Now over here, that reminds me of the power rule, so I can see this as in the form u squared. So where the derivative is drop exponent, subtract 1 from the exponent, but however, don't forget to multiply by the derivative of the expression in terms of x at the base, because that is not x, it's a function of x. So this is where we actually need to use the chain rule here. However, over here, if I look at the exponent is in fact a 2. Now, a 2 is very easy to expand and just write the expanded form of the polynomial the same way we did in the previous example, where over here we did the derivative as a first method by just expanding, and in the second one by using the product rule. So over here again, since an exponent of 2 is still practical to expand, then I could just expand that expression and then find the derivative of the terms of the polynomial one by one. Or I could use the power rule. However, if this function had an exponent of 10, for example, then in that case, expanding the polynomial is not practical anymore. You'd spend a long time expanding a function to the power of 10 that has a linear expression to the power of 10. So for that reason, it is better or more practical to use the power rule with the chain rule. Okay, so over here, I'm going to consider this as being an exponent of 10 in order to escape the possibility of being able to expand. So over here, again, I look at this in the form u to the 10. Okay, so I set the base of the power equals to u. So u is 2x plus 3. So what is u prime? The derivative of 2x plus 3 is in fact a 2 because it's a linear expression. So over here, f prime of x would actually be, now this is in the form u to the 10. U to the 10, drop the exponent, subtract 1 from the exponent, then multiply by u prime, the derivative of the expression inside. So u prime is in fact a 2, 2 times 10, which leaves me with a 20, and u, which is 2x plus 3 to the 9. Of course, we don't want to expand this because it would take us forever. It's to the power of 9, so we could just leave it as is in the form of a power. Okay, so going back to the next one. Now over here, f of x, we can look at f of x in two forms. We can look at f of x in the form of 1 over u squared, or as u to the negative 2. It's really up to you. So you could be using the expression in the form x to the n with n equals to negative 2, or 1 over x to the n with n equals to 2. So it's really up to you. I'm going to be going for this form because it would give me the expression simplified immediately. Okay, so looking at this expression in the form 1 over u squared. So looking at it in the form 1 over u squared, u would actually be negative x plus 1. So what is u prime? This again being a linear expression, so the derivative is negative 1. Now going back to the derivative of f, functions in the form 1 over u squared. If I go back to the rule of 1 over x to the n, the derivative was negative n. Now n here is 2, so it's negative 2 over u to the n plus 1. At the denominator, you increase the exponent by 1. And of course here, since I have an expression of an expression in terms of x inside the power, what you need to do here is the chain rule. You'd multiply by the derivative of that expression. So making the proper substitution, we substitute u and u prime, so that would be negative 2 over negative x plus 1 cubed times u prime, which is negative 1, which simplifies into 2 over negative x plus 1 all cubed. Moving to the next one. Now, again, the first thing you need to ask yourself, which form is this function taking? Now, by looking at this function, I know that it's in the form square root of u, where u in fact is x squared plus 1. Now, what is the derivative of x squared plus 1? U prime would be 2x, because I drop exponents, subtract 1 from the exponent for x squared, and then a plus 1, that's a constant, its derivative is 0. So going back to the derivative rule, f prime of x. Now, what's the derivative of square root of u? Now, it is in our table of derivatives, but however, if you do not remember it, you could just set square root of u in the form u to the half, and then apply the power rule for n equals to half, the same way we did here. It would lead you to the same derivative. However, you could remember that the derivative of a square root of x is 1 over 2 square root of x. So that would be 1 over 2 square root of u, and we should not forget times u prime, because we're dealing with a radicand different than x here. It's a function in terms of x. So doing the proper substitutions, f prime of x would be, now u prime is a 2x over 2 times square root of u, which is square root of x plus 1. Now simplifying 2, so that would be x over square root of x squared plus 1. Now, moving to the last set of examples we have here before we wrap up this lesson. Now, looking at this function is in form of a quotient. It's in the form of u over v. So I'd start by finding u, because we've just seen that u over v is not u prime over v prime. Its derivative is not just the derivative of the numerator divided by the derivative of the denominator. Now, we've just seen that u over v has a derivative of u prime times v minus v prime times u over v squared. Now, over here, if u is 2x minus 3, then u prime is 2. If v is x squared plus 1, then v prime is 2x. So over here, f prime of x, now according to the quotient rule of the derivative, so it's the derivative of the first times the second minus the derivative of the second times the first divided by the square of the denominator. So it's u prime v minus v prime u over v squared. Now, if you did write them in this order, you can actually see it this way. u prime v minus v prime u, and of course that's a v squared, that's not a 2. Okay, so divided by v squared. So doing the proper substitutions, u prime is 2 into 2x times v, so which is x squared plus 1, minus v prime, which is 2x into 2x minus 3 over v squared, which is x squared plus 1 all squared. Now over here, do not expand the denominator. Okay, so it's useless. Expanding it is useless. So just expand and simplify the numerator. So over here, I have a 2x squared when I expand, and I have a negative 4x squared. So that would leave me with negative 2x squared. Then plus 2 and plus 6x. So it's a plus 6x plus 2 over x squared plus 1 all squared. So that would be the derivative of f of x. Now, again, looking at this function, I have it in the form of a quotient. You can apply the quotient rule for u equals to 1. And do not forget that u prime would be 0 in that case. Okay, so in that case, u prime times v would not exist in your derivative. However, then you'd have to simplify that expression. While from the start, you can just consider it in the form 1 over u, where 1 over u, 1 over x has a derivative of negative 1 over x squared. If it's 1 over u, it's negative 1 over u squared times u prime. You'd really need to practice the rules of derivatives here. So if I look at this as 1 over u, u would actually be x squared plus x plus 1. So u prime would be 2x plus 1. Derivative of x squared is 2x. The derivative of x is 1. The derivative of 1 is 0 since it's a constant. So f prime of x, that's negative 1 over u squared times u prime, replacing u by x squared plus x plus 1 and replacing u prime by 2x plus 1. In that case, you'd have negative into 2x plus 1 over the derivative x squared plus x plus 1 all squared. However, if you have used the quotient rule in order to determine this derivative, eventually, as I've mentioned, since if u is 1, u prime is 0, then that term would be a 0. Then being left with negative v prime u over v squared, you'd actually might end up with common factors that you need to simplify. However, using the form 1 over u would give you the expression immediately simplified. Again, over here, let's just look at the last one. We have f of x to be equals to x times square root of x plus 1. Now, that does remind me of a product. However, in the first set of exercises, I had a product here that I was able to escape by just expanding in method 1 and finding the derivative of a polynomial. And over here, we've seen in method 2 that we could have used the product rule, but of course, over here, since expanding is practical, then I could just expand and make finding the derivative easier for me. However, if we look at this last one, I have a polynomial times a square root function. So over here, escaping the product is not an option. There's nothing to expand here. There's no way I could escape that product, so I have no choice but to find the derivative using the derivative rule. So I start by considering u to be square root x and v to be square root of x plus 1. So u prime is 1. Since u equals to x is linear, so the derivative is the exponent. However, regarding v prime, now if you look at v is in the form square root of u, because I do not have an exact square root of x. I have a function of x inside the square root. And square root of u, its derivative is 1 over 2 square root of u. And of course, we should not forget the times u prime here. So, however, over here, let me just use something other than u because I'm already using u for the product. Let's just call it a w here. Okay. So over here, looking at w is x plus 1. So what is w prime? W prime is 1. It's the slope of the linear expression. So the derivative would be 1 over 2 square root of x plus 1 times 1, of course, a chain rule. So that would leave me with 1 over 2 square root of x plus 1. So f prime of x, which is u prime v plus v prime u. If you have them written in this order, that would be u prime v plus v prime u. So f prime of x would be, now u prime times v, so that's square root of x plus 1. V prime times u, so u is x and this is v prime, so that would be x over 2 square root of x plus 1. Now you could leave your derivative in that form, or you could reduce to the same denominator. The common denominator is 2 over square root of x plus 1. So over here, reducing to the same denominator would leave me with 2 into x plus 1 for the first one, because square root of x plus 1 times square root of x plus 1 is x plus 1. So plus x over the common denominator, which is 2 times square root of x plus 1. Now expanding and simplifying at the numerator would give me a 2x plus x, which is a 3x plus 2. And of course, that is over 2 into square root of x plus 1, and that would be the derivative of this given f of x. Now, these are the basic rules for derivatives. However, in following lessons, we're going to see how we could find derivatives of trigonometric functions, derivatives of logarithmic and exponential functions. So we're going to be studying the derivatives of more sophisticated functions, including inverse trigo as well. Okay, so that's it for this lesson, and I'll see you in the next one.